So for the last lecture of this week, we will look at some examples of programs in Haskell to get used to the idea of programming in this language. Before we do that, we will revisit a couple of the notions that we have seen for writing Haskell functions and explain a few concepts that we did not do when we introduced them. So we begin with pattern matching. So remember that in Haskell functions, we can use patterns to illustrate cases. So here is an example of the AND function. So the AND function does a pattern match on the first argument. If the first argument is true, then the first definition is used. And in this case, it returns the value of the second argument. If the first argument is false, we already know that the answer is false. So we can ignore the second argument and just return false. So here we have true and false as constant patterns, and B is a usual kind of pattern which is matched by whatever it invokes. Now one thing to notice in this is that the value B that we write here in the two definitions actually has two different uses. In the first case, the value B is important because whatever we feed as B to AND comes back to us as the output. So it's important to connect the output B to the input B. The B in the answer is the same as the B that is given as input to AND. On the other hand, in the second case, we see that this particular thing gets discarded because we don't really care what B is. False and anything is false. So the answer is immaterial, the value of B is immaterial, the answer is independent of B. So Haskell then asks why we need to provide a name if we are going to ignore the argument. So there is a special notation in Haskell which allows us to specify a wildcard. Okay? So this symbol underscore denotes an argument which matches everything. So it's like using a variable. Remember, a variable matches everything and it will be substituted by the value you provide. So the difference between a wildcard, which is a don't care kind of argument, and a name like B is that the value you give is going to be thrown away. So any value matches our underscore, but the value is not captured, cannot be reused. But two things. One is it avoids unnecessarily putting a name in there. We don't have to think of a name. Second thing is that it makes it also transparent that this function really does not care about the second argument. So from the point of view of reading the code, it's immediately obvious that AND with false in the first argument does not require the second argument to give its answer. So here is a more extreme version of that. Here is the version of OR that we had written, but now with these wildcards. So OR says that if the first argument is true, it doesn't matter what the second argument is, the answer is true. Similarly, if the second argument is true, it doesn't matter what the first argument, the answer is true. And now if we have skipped both of these, no matter what I give, the answer is false. So the last definition on its own would be totally useless. But because it comes after the first two definitions, right? So we have already gone past these two cases. We know that this must be false and this must be false in this case. But what it says is that if I have reached here, at this point, if I have reached the third line and I have not matched the first two lines, then no matter what the value of the two arguments, the answer must be false. Notice we are using two underscores in the same definition. So it's really emphasizing the fact that underscore is not a name of a value. We cannot write two arguments with the same name in a normal definition because then there would be confusion about which value we are referring to if we use it on the right hand side. So if we say plus mn, we can't write plus xx because we don't know on the right hand side which x we are going to use. Whereas if you use underscore, you cannot use the value on the right hand side. So you need only one underscore across all definitions because it's just going to be a value that is ignored. The other new concept that is useful to use is to do with conditional definitions. So here is a variation of our factorial function which handles negative numbers. Earlier we had given factorial 0 as a pattern match. So we had written something like factorial of 0 is 1 as a separate case, and then we had written this conditional thing only for n greater than 0 and n less than 0. But we can as well use the conditional to give a completely conditional definition. So this, in a more conventional language, will say something like if n is 0, then the answer is 1. Else, if n is greater than 0, then the answer is n into factorial n minus 1. Else, if n is less than 0, then factorial is the value of factorial minus n. So now notice that we are forcing ourselves to give a guard for each case. And in particular, we might reach a situation where we wonder whether there is a value of n. This here we can check that n must be 0 or greater than 0 or less than 0. But if it were a more complicated situation, it may well be difficult to determine whether every input actually matches one of these things. So have we really covered all the cases? Or is there a situation where we have missed something, in which case some inputs might give us some error about pattern match failures. So the equivalent of the else in a normal programming language. So normally we say if condition 1 then something, else condition 2 then something, and so on, and finally the last one is a catch-all else. So here there is a catch-all word called otherwise. So instead of saying explicitly that the last case is n less than 0, we can use this word otherwise to say that if it is not 0 and it's not greater than 0, then do this, right? So otherwise is a special reserved word in Haskell, which is a condition which is always true. So if we reach the otherwise condition in a sequence of guards, then that guard will always evaluate to true, and whatever definition this provided with that guard will match. Right? So this ensures that every invocation will match at least one of the definitions in a conditional. So we have these two new things. We have these don't care patterns and otherwise, and we will use these to simplify some of the code that we will develop in the examples this time. So let's look at our first example. The first example is a very traditional example and one which illustrates many interesting concepts in programming in all languages. So this is the GCD algorithm. So remember, the GCD of A and B is the greatest common divisor. It is the largest number that divides both A and B. And since 1 definitely divides both A and B, this is always well defined. It is at least 1. So if the GCD is 1, then they are said to be co-prime. So assuming that A is the bigger of the two numbers, right? Then what Euclid proposed was the following algorithm, which is that we keep replacing the GCD of AB by the GCD of the smaller number and the remainder of the larger number divided by the smaller number. So for instance, if we start with the GCD of say 18 and 12, okay, then this will say replace this by GCD of the smaller number, and the remainder, if I divide 18 by 12, I get 6 as the remainder, because it's 1 with the remainder 6. Then I will get GCD of 6, and the remainder of 12 divided by 6 is 0, and then this will be the base case, and this will say that the GCD is 6. Right? If B is 0, the answer is A. So this is Euclid's algorithm. We will not worry about its correctness, but it is useful for you to think about why this works. But it keeps reducing GCD to smaller and smaller numbers, and you're guaranteed that it will terminate. In fact, it's a very efficient algorithm. It turns out to be proportional to the number of digits, so it's actually a linear algorithm in the size of its inputs. So this is a very simple function to code in Haskell. So GCD, first of all, takes two integers, right, and produces an integer. So that is the type. So the base case is easy. GCD of A and 0 for any A is just the value A itself. Then if we assume, as we have done here, that A is greater than B, then we take the GCD of the smaller number, and we have the mod function which gives us the remainder. So it's the GCD of A and B, if B is not already 0, is given by GCD of B and the remainder of A divided by B. And in case it turns out that this assumption is false, so we actually have A less than B, then we just reverse it. So here we are using this new word that we have discovered called otherwise. So if A happens to be smaller than B, then we just invoke GCD in the reverse order. After that, notice that since B is the smaller number and the remainder will be smaller than B, all successive calls to GCD will have this property. So only the first call which may be wrong, in which case we reverse it. So this is like our earlier case where we said factorial of a negative number can be fixed by taking the negation of the argument. So here is another example. Supposing we want to find the largest divisor of n other than n itself. So of course n divides n, but then other than n, what is the next smallest divisor? So here is a simple strategy. We know that 1 divides n. So 1 is certainly a candidate. Just like in GCD, we know that 1 is a GCD, so 1 will always work. So here we can just iteratively try n minus 1, n minus 2. So we go back, we want the largest one. So we go back in reverse order from n. We start with n minus 1 because we don't want n itself. And we check for each of these. So it's just in normal programming, this would just be a loop. Right? You're just trying for each I from n minus 1, n minus 2 down to 1. If I divides n, then we stop and report that. So this loop can be simulated using a simple recursive call. Okay? So we say that, so the operative thing is actually the second function. So here is an example where the function we want to write is expressed in terms of another function. So the largest divisor of n can be obtained by searching for divisors of n starting from n minus 1. And how do we search? Well, if we get an answer, if the second argument divides the first argument, so if m divided by I is 0, then we have found the argument, so we return I. So this means that I divides m. We're done. Okay. Otherwise, we will go to the next one. And the reason this terminates is that eventually I minus 1 is going to become 1 and 1 will always divide. Okay. So we have an auxiliary function. So this is something about Haskell. You can write a bunch of functions together. It doesn't matter in what order you write them. It doesn't have to be before or after. And these functions can call each other. So we have largest divisor, the function we want, which calls this divisor search. And divisor search is the interesting thing about divisor search is a kind of recursive version of what we would normally call as a loop. So it's looking at I, and if it's not I, it's going to I minus 1. Okay, so we know what a logarithm is, right? The logarithm tells us what power we need to get back to the number. So the log to the base k of n is y, provided k to the y is n. Another way of thinking about this is if we start with n and then we divide by k and then we divide by k and so on, how many times can we do this until we reach 1? So usually the logarithm is some fractional number. So let us do a simpler version which we call the integer logarithm. Okay? So the integer logarithm is a number such that if we divide by that number, we stay above 1. If we divide by one more number, we go below 1. So this is the integer part of the actual logarithm. Okay? So as an example, if we take the base 2 and we take the number 60, then the integer log is 5, because if we divide 5 times, then we stay above 1. 2 to the 5, by the way, you should know, is 32. Right? So 60 divided by 32 is more than 1, but 2 to the 6 is 64. So 60 divided by 2 to the 6 will be less than 1. So therefore, by our definition, 5 is the largest number of times we can divide by 2 and stay above 1. So this gives us a strategy to compute the integer logarithm. We start with n and we keep dividing by the base k until we reach 1 or go below. If we reach 1 exactly, then we get the exact logarithm. So for example, if we had done integer logarithm 64, then we would have got 6, and this is exactly because 64 divided by 2 to the 6 is equal to 1. But because we started with something which was off that, we got something which went below 1. So either we reach 1 or we go below. So here is a function. It takes, here now we should be clear that this is the base and this is the number. Right? So the first argument to integer log, because of the way we write it, we write int log of the base of n. So k is the base, 1 is the number. So anything raised to 0 is 1. So if we get the number 1 as our input, then the base, with respect to base k, the integer logarithm is always going to be 0 by definition. Otherwise, provided we can divide it, right? So provided n is bigger than k, we go ahead and divide it, right? And then we compute its logarithm. So it's a recursive algorithm. We keep dividing, and notice that we don't need to actually divide exactly. It's enough to do an integer division. Okay, so we go from 60. In our case, we go to 30 over here, right? Then we would go to 15, and now if we divide once more, we would go to 7.5, but it's enough to go to 7. And then go to 3, and then go to 1, and then stop. Okay? So this is how it works. Okay? So we went down 1, 2, 3, 4, 5 times, and at 5, the 6th time we would go below 1, and therefore we would stop. Right? So this is the integer logarithm function. It just does this divide by n, dividing n by k until we reach 1 or go below. So for a change, let us look at a function which has nothing to do with numbers per se. It's more like something which manipulates sequences of characters. So we want to reverse the digits of a number. Of course, we will do it numerically, but later on we will see how to treat these as lists and do it in a different way. So we want to write a function int reverse, which will take a multi-digit number and return the digits in reverse. So if we give it 13276, it should give us 67231. So how would we do this? So here is a strategy. Okay? So if we take 13276 and we divide by 10 using integer division, then we get 1327, right? And we take its remainder with respect to 10, we get 6. So using div and mod, we can split this number into the last digit and the rest. Now, using the style that we are used to in Haskell, we will do something inductive. So we will reverse the first part. Okay, this is a smaller number. So here the induction is on the length of the number. Earlier our induction used to be on the argument itself. We do n in terms of n minus 1. Here the induction is on the length of the number. So we will see that for things like lists and sequences, the length is something we can write inductive definitions based on. So if we inductively assume we know how to reverse this number, then we will get the last part. So this 7231 has now been recovered. Now we need to stick a 6 in front of it. Right? So how do we get 6 in front of it? We have to shift 6 to the left, which means we have to pad it with zeros. Okay? So we have to multiply 6 by a suitable power of 10 and add it. So we have to take 6 and make it 60,000 and add it. And the question is, how do we get the suitable power of 10? Okay? So it turns out that the suitable power of 10 is just the number of digits that we have here. So in this case, if we take the integer logarithm of this, it is just 1 less than the number of digits, right? If we divide this by 10 4 times, we get 6.7 something, okay? And if we divide it by 5 times, we get 0.67 something. So if we take the integer logarithm, it is precisely 1 less than the number of digits in the decimal number, and that's precisely the number of times we need to multiply 6. Okay? So we can use the function we have defined in the last example in order to get this last step done. So here is the function. Okay? So it says that I want to reverse an integer. If the number is a single digit number, if it is less than 10, I do nothing. Otherwise, I recursively reverse the first k minus 1 digits. Okay? Then I take the last digit and multiply it by suitable power. The suitable power is the integer logarithm to the base 10 of the original number. And how do I define power? Well, we saw in the first few examples that plus is repeated successor, mult is repeated plus. So power or exponentiation is repeated multiplication, right? If I say 2 to the power 7, it means 2 times 2 times 2 times 2, 7 times. So that's exactly right. We wrote plus and mult. We can write a power function which says anything to the power 0 is 1. And if something to the power n is m times m to the power n minus 1. So this is saying m to the power n is equal to m times m to the power n minus 1. Right? So using this function and the int log function that we wrote last time, we can compute the reverse of any set of digits. Right? So what we have seen is a bunch of examples, but along the way we have also looked at some new syntax involving function definitions. One is this underscore as a don't care pattern, which allows us to specify arguments which are not used in evaluating the function. So it also makes it gives us two options. One is not to use a variable where we don't need it, and second, it makes it more transparent that a function is independent of a particular argument. The other thing is that in a conditional definition, we can use otherwise as a catch-all phrase at the end to make sure that any argument which does not match any of the previous conditions will definitely match this one. So this ensures that we don't have any pattern match failures.